Hello, welcome back to everybody. This is the sixth video from the series which is dedicated to my project, a tube stereo receiver, which I'm currently designing and building. As you remember, in the last video I showed you about the first successful fire up of the tube amplifier section. Now in this video I would like to go a little more in deep with that. And I would like to report, first of all, about the improvements, the further improvements I have implemented, some fine-tunings as well on the tube section, on the tube amplifier section. And secondly, I would like to report about all the tests I have been doing in order to check the performances of the newly built unit. So I hope you enjoy the video. Thank you very much. In order to properly describe the tube power section, I would like to start from the global schematics. You might remember this. So on the top left, you can see the power module. We have commented already. You see the arrow, the yellow arrow. And then below, going below, we have all the inputs. So the Bluetooth receiver module, the FM tuner module, and the digital to analog converter module as well. And also we have an auxiliary input. Then going to the right, we find the input selection unit, which will be built, the tube preamplifier section, and the power amplifier section, the tube power amplifier section. Everything will be managed through Arduino microcontroller. So let's go a little more in deep on the power amplifier section. During this presentation I will utilize this simplified schematics for the power tube section. But I think it can give anyway a good idea of how the amplifier is working. As you can see, the first stage is a gain stage based on the EF86 tube, which is a penthode, here utilized as a triode because I don't need so much gain. So as you can see, the incoming signal, this is a very simplified 1 kHz sine wave, the incoming signal is then again amplified by the EF86 tube. I can find my amplified signal at the output, so at the anode of the EF86 tube. And as you can see, the phase is exactly the opposite than the incoming signal. Then my preamplified signal by the EF86 tube is fed into the second stage, which is the phase inverter or phase splitter. This stage has two roles. The first is to provide additional gain in order to properly drive the output tubes, and the second is to create two versions of the output signal, one exactly the opposite phase than the other. So in this picture you can see my preamplified incoming signal into the phase splitter, and here you can see the first of the two output. This is the output of the first of the two tubes within the phase splitter, and this is the other signal. As you can see, the two signals are almost identical, just the only difference is the phase. The second signal is exactly the opposite phase than the first signal. And here you can see another view of the two signals coming out from the phase splitter. This is exactly taken from my amplifier, from my working amplifier. Then I have the third stage within the power amplifier, which is the power tubes section. The role is, of course, to provide additional amplification in order to properly drive, first of all, the primary winding of the output transformer, and then my speakers. In order to do that, as you remember, I had the two signals at the output of my phase splitter. As you remember, one the opposite phase than the other. Those two signals are fed into the inputs of the two power tubes. In this way I can achieve a greater efficiency than the typical class A amplifier with just one tube. If you look at the current variation at the cathode of the power tubes, which we can say is very similar to the current variation at the primary windings of the output transformer, you can see a very similar behavior, a very similar signal than the incoming two signals into the two power tubes. This is a low power situation where the two power tubes behave very similarly. Each one of them amplifies the whole signal. This is very similar to class A, and again is typical of low power situation. If I increase the power, you can see this behavior where the lower part of the waveform is somewhat compressed. And this is the typical behavior of the push-pull amplifier, where each one of the two power tubes takes care of a portion of the incoming signal. Then the two signals are then, I would say, sort of combined by the output transformer, and I can find my very beautiful sine wave at the output of the output transformer, and this is the signal which is then fed into the speaker system. So we have understood that this amplifier is a class AB amplifier. As you have seen, each one of the two tubes amplify the whole waveform, the whole signal for low power levels, so their behavior is very similar to class A amplifier. So we can say the amplifier is class A for low output levels. If we increase the output level, the output power, till the maximum, which is 32 watt output power, then in this case each one of the two power tubes takes care of a more limited portion of the waveform, and the output transformer combine the two contributions into a very clean, very beautiful output signal. Final part of the tube output section schematics worth mentioning is the feedback loop. As you might remember, I initially decided not to implement any feedback. The original version, the initial version of the amplifier was a completely open loop, but then after some careful listening tests and some also measurements, I decided to implement a little bit of feedback. So in this case, as you can see, there is a connection between the output from the output transformer and the first gain stage. This connection is implemented by means of a resistor and the capacitor. The value of the resistor and the capacitor is very important, as we will see later. So after a little bit of analysis of the tube power amplifier section, let's now see how the performances were measured. I utilized a signal generator. It was configured to generate, for example, a sine wave of 1 kHz frequency, or square wave, or sine wave with different frequencies in order to test, for example, the frequency response. This signal was fed into the first gain stage of the power amplifier. And then, in order to check the power tube performances, I measured the signal I have at the output of the output transformer. I utilized, of course, a dummy load, which is basically a resistor, a big powerful resistor, in order not to utilize the speakers. Otherwise, the sound would be too high for my ears. In this way, by means of oscilloscope and distortion analyzer, I could measure all the specifications of the signal I have as the output of my power amplifier. So, having said all that, let's see how the amplifier behaves. And I can say it behaves pretty well, I would say. So the first measurement was the distortion. The first parameter which was measured is the distortion. And as you can see, the distortion is 0.13% at 1 watt output power. Which is very good in my opinion, considering this is a tube amplifier. The incoming signal amplitude is 98 millivolt peak to peak in order to achieve 1 watt output power. The second measurement was the frequency response measurement, and as you can see is pretty much flat. There is a little bit of roll-off on the very high frequency from, I would say, 15, 16 kilohertz. And this is something I wanted to achieve. As you can see, it's just minus 1 dB at 20 kilohertz. This is for stability, as we will see later. And again, this is something I wanted to implement in order to somewhat limit the passband of the amplifier. Again, -1 at 20 kilohertz is very good. Also, as you can see, the response at the bus frequencies is very good as well. So the passband is flat, starting from 5 Hz, which is really very good, and this is also due to the very high quality output transformers. The third measurement was the maximum indistorted output power. This is 32 watt in one channel, and a little bit, there is a very slight difference between the two channels due to the tolerance, I would say, of the components. So one channel is 32 watt, the other channel is 32.8 watt. In order to measure that, we start from the amplitude of the output signal, the peak-to-peak amplitude, and starting from that we can calculate the output power. As you can see, this is the maximum amplitude of the signal immediately before the distortion could somewhat change the waveform. Let's go back one moment to the feedback topic. This is where I operated much of the fine-tuning and following listening sessions of the amplifier, and also, of course, measuring sessions. So, as we said before, feedback can improve the performances of the amplifier. In particular, it can reduce the distortion, it increases the linearity of the passband, of the frequency response. It also reduces the gain. This is not a problem in my case because the amplifier had much gain since the beginning, so the reduced gain is not a problem. Also, as the gain is reduced, also the signal-to-noise ratio is increased. So is everything good with the feedback? Well, yes and no, because if we increase the feedback too much, the amplifier can become unstable. So it's very important to carefully fine-tune all the components related to the feedback loop. Here you can see the distortion performance of the amplifier without feedback. So this is the original version of the amplifier without any feedback loop, so completely open loop. As you can see, the distortion was 0.22%, so it was higher than the actual distortion. And as you can see, 1 watt output can be reached with just 35 millivolt peak-to-peak signal. Here you can see the situation after applying 9 dB of feedback. So this is the final situation we have seen already. So we have now 0.13% distortion, so more or less half of the distortion. As you can see, the gain decreased after applying 9 dB of feedback, because now we need 98 millivolt input signal peak-to-peak in order to reach 1 watt output. In this picture you can see the positive impact of the feedback on the linearity. The blue line is the frequency response without any feedback. As you can see, we have a little bit of non-linearity, plus 2 dB minus 1 dB, more or less. And as you can see, the more I apply feedback, the more the frequency response becomes closer to the flat pass band. The final frequency response is the red one, which is the actual one we commented already, and this is achieved by applying 9 dB of feedback. With these pictures, I would like to show you the role of the feedback capacitor. This is a very important component for sake of the amplifier performance, and it's in the feedback loop. So as you can see in the upper left picture here, I have the square wave response after I applied 9 dB of feedback. As you can see, there is a little bit of sign of instability. Well, not instability, but some little bit of ringing. You can see some spikes here in the picture. So in order to correct this, because this might sound a little bit harsh, so in order to correct this, I implemented a capacitor in parallel with the feedback resistor. It's very important to apply the correct capacitance. If we apply too much capacitance, as you can see in the lower left picture, in this case this is 1000 picofarad, in this case you can see that the waveform is a little bit distorted. So this means that I applied too much attenuation of the highest frequencies, and this is not good because this can impact the frequency response. In the lower right part of the screen you can see the corrected waveform. I implemented 175 picofarad capacitor, and this is the perfect value in this case. This value highly depends on the particular output transformer which is deployed. So it's very important to carefully check and find the correct value based on the single amplifier, on the single unit. Here I would like to show you some other, let's say, additional improvements I have implemented on the amplifier. Again, following listening tests, measurements, and also following assessment on how the amplifier is working, with mainly durability and reliability in mind as well. So the first improvement is to migrate to alternate current heaters. You might remember I initially deployed DC heater because I would like to provide the maximum signal to noise ratio. Then I attempted to power all the smaller tubes heater with AC, with alternate current, and I saw that even in that case the amplifier is really dead quiet, with no sign of hum, no sign of whatsoever noise coming from the speakers. I think this is because of the star grounding layout, and also because of all the solutions implemented, which we discussed in the past. So again, even after migrating to AC heater, the amplifier is again dead quiet. So I decided to stay like that. In this way, I got an increased efficiency, a lower heat inside the chassis, because of course I don't need stabilizers for the voltage anymore. So in this case, again, the amplifier is working much cooler inside the chassis. Another, I would say, improvement for sake of reliability of the amplifier is to slightly decrease the value of the tail resistor in the phase inverter. I measured, in fact, the DC voltage at the cathode of the two sections of the ECC81 tube, and I saw that they were approaching 90 volt, which, as you can see, is exactly the limit of the maximum cathode to heater allowed for this kind of tube. So I slightly decreased this value, the value of this resistor, and in this way I achieved something like 75 volt at the cathode of the two sections of the ECC81, and so it's a much safer situation, and yeah, it's very important every time you are dealing with such schematics. It's very important to double check the cathode to heater maximum voltage. All the numbers we have seen till now, and all the theory, are very interesting, I bet. It's the same for you. But then I think the main question is how does the amplifier sound? Believe me, the amplifier sounds very well. I'm coming from extensive listening sessions, adjusting sessions, and following listening again. And I can say that I'm very happy about how the amplifier sounds. It sounds so good, in my opinion. Let's I would like just to propose you some music now, just for you to appreciate how the amplifier sounds. Of course, it's not like the real thing for many reasons. The microphone, the microphone placement, the speakers, the room where I am, so everything is not ideal. So again, it's not like the real thing, but yeah, anyway, I think it can give you a proper idea of how the amplifier is working. So, as you have seen, everything is beginning to take shape, I would say, in a proper way. Thank you again for your attention, and see you in the next video. Thank you very much. Bye.